Hello, my name is Camilo Vazquez. I'm a senior undergraduate physics major at Stevens. I was part of the NAC this summer, working at the VLA in Socorro, New Mexico under my mentor, Dr. Pallavi Patil. And my research was on multi-frequency imaging of kiloparsec scale jets and obscured radio powerful quasars. So let's just jump right into the background science of my research. So first off, it's important to understand what an active galactic nuclei is, or AGN for short. So an AGN is just an accreting supermassive black hole at the center of a galaxy. And oftentimes these black holes have bipolar jets made up of relativistic particles shooting out of them. And these jets eventually over time escape their host galaxy and produce radiolobes when they hit a denser medium. And what these radiolobes are is they're essentially just hotspots of gas that emit most powerfully at radio wavelengths, and they expand sort of like balloons. AGN also vary in their brightness, and we can measure this variability and then use this variability to calculate an upper limit on their size. And the best upper limit we have right now is about 10 to the negative 4 parsecs, which is about the size of our solar system. Also, the typical luminosity of an AGN is about 10 to the 38 watts, which is about the same as 2 times 10 to the 10 solar luminosities. And to put this into perspective, we're talking about an object that is about the size of our solar system that can emit light comparable to a galaxy. There are also several subclasses of AGN, such as quasars, radio galaxies, Seyfert galaxies, and blazars, and there's many more. But the one I'm focusing on are quasars, more specifically, heavily obscured and young quasars. So what a quasar is just a hyperluminous AGN. And they're hyperluminous because the accretion onto the black hole is very efficient, and thus the luminosity is that much greater. And when the host galaxy of an AGN or a quasar goes through a merger, the dense gas and dust can present a significant obstacle to the central AGN, as well as its jets, if the jets are young enough to be still within the host galaxy. And that's what my research is looking to investigate. We're trying to investigate whether these jets can have an effect on their host galaxy and the star formation rates and the evolution of its host galaxy. In order to do that, it's important to look at quasars that are in a very unique and brief stage of their lifetimes. So here I have a sequence of images that illustrate the different phases of the host galaxy and the quasar. And the phase I will be focusing on is the blowout phase, which is when the jets are young and compact, and the supermassive black hole is rapidly growing within the host galaxy. This AGN then interacts with its host via its jets and radiative winds, and in turn expel the gas and dust present in the galaxy. And what this does is it could alter the evolution because by expelling the gas, you expel the fuel that allows star formation rates to increase or to exist at all. So this image can put these heavily obscured quasars and the rolling galaxy evolution into perspective. And in order to investigate quasars in this phase, we must look at a multitude of them in a sample of sources that exhibit the characteristic qualities of a blowout phase galaxy or quasar. So that brings me to the sample I worked with this summer, which is the sample constructed by Dr. Carol Lonsdale in 2015. The sample makes use of WISE, NVSS, and SDSS data. And the way the sample selection process goes is pretty simple. First, you select sources that are bright at 22 micrometers and also have very red WISE mid-infrared colors, and then cross-match these sources in NVSS to make sure that they are bright and unresolved at radio wavelengths. And then finally, these cross-matched sources are inspected in SDSS to ensure that they are either optically faint or undetected. And what that does is that you're ensuring that you're looking at quasars that are obscured or at high redshifts, because if you have quasar, they're so bright, you would definitely expect to see them in SDSS, especially if you know where they're going to be. And if you look at that spot where you know they're going to be and they're not there, or they're very faint, that's a very strong sign that they're being obscured. So let's talk about what's in the sample. This sample contains 156 quasars that are at redshifts between 0.5 and 3. These sources are believed to be the result of a recent gas-rich merger, igniting an AGN and a starburst phase. They are likely to be in a blowout phase where AGN and radio jets are interacting with host, as I discussed previously. So in order to understand the radio properties of the sample, there was also a follow-up survey using the VLA at X-band or 10 gigahertz in snapshot mode. This survey revealed that 80% of the sample has compact radio morphologies, which just means that the sources have a linear extent of about, or have a linear extent less than a few kiloparsecs. We also looked at the radio spectra by combining different archival surveys. And here's one such example on the right. And the key result is that about 57% of the sources show peaked or curved spectra, which is consistent with what is seen in young radio AGN. In order to investigate these radio sources in more detail, a subset of 20 sources are being followed up with VLA and VLBA. Here, my focus is going to be on one of those sources, JO404-24, and this source is a 6 kiloparsec source with 2 lobes. It also shows a dense interstellar medium and a broad CO line when observed through ALMA. And the goal is to eventually compare the ALMA maps of the interstellar medium and molecular gas with my VLA spatial and spectral maps of the source JO404-24. So let's go into the actual imaging I did for my research. So in order to create images, I used data from VLA observations made at multiple frequencies. The frequencies used were L, C, X, U, Ka, and Q band, or 1 to 50 gigahertz. The VLA was an A configuration for these observations, and the total observation time was about 4 to 5 hours. I used theoretical noise values calculated by my mentor, and these helped for setting the signal to noise ratio for T-clean and self-calibration, which I will talk more about soon. And the goal of these observations were to obtain deeper images at different bands to probe morphology at different scales, as well as to create spectra with better sensitivity. So here's just a quick little flow chart showing how the image processing went. So as you can see, I initially ran the raw data through the VLA calibration pipeline, which is just a chain of calibration tasks that are run sequentially and automatically. And then I ran my corrected data through T-clean, which is a task in CASA that cleans and deconvolves images. And then after getting an initial image with T-clean, I then apply phase and amplitude calibration to the data and repeat until the signal to noise ratio has reached a satisfactory value. And then finally, I got the clean images that I'm going to show you now. So as you can see, there's 4 images here, an image at L band, C band, X band, and U band. And excuse me. Clearly, as the frequency increases from L to U band, you can see that the resolution increases. And if we start at L band, we can see that we're just looking at a point source. The resolution just isn't high enough to see any structure. But at C band, you can start to see lobe separation. And I've labeled the lobes L1, L2 respectively. At X band, you can see more lobe separation, and you can start to see a little bit of the core. And then finally at U band, you get a nice image of the 2 lobes and the core taking central position between the 2 lobes. Another interesting thing to note is that there's also possible jet emission. If you look between L2 and the core, you can see a little streak of pink, and that may be a sign of jet emission, which will be something that we'll investigate further in the future. So here's the Ka band image. So some people might have been wondering why I don't have 2 extra bands images for Ka band and Q band, and that's because at such high frequencies, the emission of the source is actually just too low. So if you look at the spectra on the right, which is another spectra constructed from archival surveys, you can see there's possibly a spectral break, which is just a property of synchrotron radiation. And what spectral breaks are good for is that you can calculate ages from them, which would be something really interesting to do with this source in the future. So let's move on to the spectra that I constructed. So as you can see, there's a spectra on the left, and then there's a corresponding radio image on the right. So it's color coded. So on the right, you can see what each curve corresponds to on the image. And the gray curve on the left is the overall spectra of the target. And then the 3 colored curves below are the individual spectra of each component. And as you can see, the 2 lobes, the blue and orange curve, have steep spectra. And then the flat spectra, the green one, is the core. This is something you would expect to see in an AGN. Typically, the lobes have steep spectra, and the core has flat spectra. So let's move on from here, and we can now go on to the next steps from my research, as well as a summary of what I've done. So the first step would be to apply flux limits to the Ka band data, and then utilize the likely spectral break that is there to calculate the age of the source. And then after that, I would like to obtain a spectral map of the target. So to explain what a spectral map is, we look on the right. These are each in-band spectral maps of the source. What I would like to do is create images like these, but across multiple bands. So most likely across X and U band. I would then like to expand the analysis to the rest of the subsample, and then eventually establish the evolutionary stage of each source and its relation to its surrounding environment. And finally, in summary, this sample catches quasars in the perfect evolutionary stage to find jet interstellar medium feedback. 80% of the sample is compact, and the majority show peaked or curved spectra, and according to the follow-up survey. And multi-frequency imaging reveals double lobe and core structures in J0404 -24. Spectral analysis shows a possible spectral break at Ka band, which could be used to calculate an age. And by probing morphology and the spectra of the sample, we can help investigate the effect of young jets on galaxy evolution and star formation. Thank you very much.
Thank you so much, Camilo. This is great. I mean, even like I saw you submitted a paper already with this, which is very impressive. So congratulations.
Thank you.
So we have time for maybe 2 questions or more.
I have a question to Camilo, and I'm sorry, like I missed a bit of your presentation, so I'm not sure if you covered that already. But when you showed the graph where you have the 2 lobes and the core, the one before does that, like, especially like the one for the lobes, does that like say something about the age of the AGN?
Like the slope of the spectra?
Yes.
Sorry, can you say that again?
Yeah, the slope of the both the lobe 1 and 2. Does it tell something about the age of the AGN?
I think I could if I had more data at higher frequencies. Again, I would probably just need a spectral break, and in order to see, I need to get flux data at Ka band, which I just don't have. So if I was able to get flux data at that higher frequency, I'm sure I'd be able to calculate an age for each of the components as well.
Okay, thank you so much.
Nice talk, Camilo. I just was curious, when you were reducing the data in the different bands, did self-calibration have more of an impact in one band than the other?
Yeah, so, well, yeah, it definitely depended on the different bands. So some bands would I guess respond a lot more to the self-calibration. So at the higher frequencies, I would only be able to do 1 round of self-calibration, whereas at a low frequency, I would actually be able to do like a couple rounds. So it definitely depended on the frequency band.
Great, thanks.
Well, thank you, Camilo, again for your talk.